Hello and welcome back to Differential Equations, section 2.2 on equilibrium solutions and stability. In your previous mathematical life, you were introduced to basic equations, and those basic equations had numbers as the solution. Here's a tough one, x plus 3 equals to 5. And as you solve this, you get x equals 2, and you knew exactly what that meant. Right, 2 was the solution. If it was a part of the word problem, you can just say, 2 people or 2 desks or 2 trees, and you're good to go. You can graph it easily on the number line, right? You have your 0, 1, and then 2, and there it is, right? So it was very, very simple. When you enter the world of differential equations, however, your solutions get to be way trickier because the differential equation has as its solution either a function or an expression in implicit form that is not a function. Now, some of those solutions are easy to follow, and you can use them easily to compute the model. We dealt with those population models last class. And with those solutions, we say those are stable. Those solutions, you can always plug in the time, compute the population. If you have a population, you can compute the time, right? There's a one-to-one correspondence there when you take the limit, right? So let's first take a look at the population models. We had 2 population models that we covered somewhat in depth. The first one was the differential equation dp dt equals kp, whose solution was p of t equals p0 e to the kt. Now, when you use this particular solution, you can compute the population, or you can compute the time if you have the population. And when we took the limit as t goes to infinity of p0 e to the kt, we found that positive infinity was a solution, and we were not happy with that model because the model like that would say that there is infinite population on the finite surface area of a planet, let's say, or 10 planets, I don't care. Can't have infinite number of people on 10 planets either. So we have to now separate the idea of what the model represents and how good its solution is. This solution is perfectly good, right, for the differential equation it came from. And we can analyze the parts of that solution and then say whether the model itself fits the observed phenomena. But the solution itself, if you are using it to compute values, regardless of how well it reflects the reality, the solution itself, when you compute the values, right, you can always compute. You plug in t, you can calculate p. If you have p, you can ln both sides and get the t out, right? So it's a good solution. The other example that we had, where the population was the birth function minus the death function times the population, which was the second example, gave us that a logistic, right, growth equation. Now we did dp dt is equal to what was it? P minus bp squared, right? Was that the one? Which eventually led into the logistics equation problem, where we had that p0 divided by p0 plus m minus p0 e to the kmt. Let me actually, because when I need this, I derive it. Yeah, I got it. That's it. So they use minus, but if you don't have a minus, the calculation would give you minus when you try to calculate k. And all of these formulas here that you see are from the same family of differential equations. So all of these, this one, and this one, belong to the same family of dp dt is equal to some function of time. And, sorry, some function of population, not time. Function of population. And those systems are called autonomous first-order differential equations. So that's the form. Now, what they do is they actually use in the book dx dt is equal to f of x. Now, it's important to understand that x is some function of t, whether it's implicit, explicit, right? It's something like that. And now, since we know, I'll add this as a note on the side. I did ask you about it. Note, from Calc 1, we know that critical point is a point where is a point, let's say, is a point x, t equals c, or no, x equals c, sorry, x equals c, where f prime of x is equal to 0, or f prime of x dne does not exist. So that's the side note from Calc 1. We did review that earlier before we started the lecture. So now, if I want to find a critical point of the differential equation, it should be clear that I am setting f of x to 0, right? Because that's actually the derivative equals to 0. So, critical point, I'm writing this in blood, which means it's insanely important. Critical point of autonomous DifEq is given by f of x equals 0, because that is equivalent to saying dx dt equals to 0, because there is equal sign in between them. So, further, if x equals c is a critical point, of dx dt equal f of x, then the differential equation has the constant solution. X of t equals c. should I even dare and say, no, I should dare and say it's common sense. Because if your x equals c is the critical point where this is equal to 0, then you have the derivative equal to 0. You integrate both sides. Integral 0 is 0 plus c, and there you go, right? So you integrate both sides, you get x equals c. 0 plus c, which is c. So that makes perfect sense that if it is a critical point, right, then the solution is just a constant. Maybe we should write it just because we can. I'll put it as a note. You have your dx dt equal 0, then separation of variables dx equals 0 dt. Integrate both sides, x equals 0 plus c, x equals c. Right, so at this point, after Calc 1, Calc 3, and now DifEq, that statement should be common sense. And this solution, right, is sometimes called, what they say, equilibrium solution. So this solution is sometimes called equilibrium solution. What does that mean? Well, think about it. If you have a constant population, right, the amount of people born is the amount of people dead in every year. So it's a wash, right? That population doesn't change. It's a constant population, and we call it equilibrium. What happens when you offset the equilibrium? Population either goes up or population goes down. There are few nations now in the world whose population is going down. Japan, Germany, we started in US to also lose population due to less kids. So when you take a look at the population, since you have some nations that are rapidly developing population, and you have some nations that are declining in population, where in between those two states, there has to be a state where the population is flat. No increase, no decrease. The amount of people dead in a year is the amount of babies born, and it's just on a standstill. That is called equilibrium, right? Now you are used, if you took physics, you are used to equilibrium position being the one where the system is in its minimum energy state. So equilibrium for a spring is when you have a spring and you just not touching it, you just put it on a desk, and the original length of that spring is whatever it is, and that is called equilibrium state. Then you can go and harass the spring by either squeezing it or stretching it, right? Then you are taking it out of its equilibrium state by pouring energy into the system. And what is spring trying to do? Spring is trying to oppose whatever you do to it because it wants to go to its default original state. For humans, being lazy is equilibrium state. Sitting on a couch doing absolutely nothing or being passed out drooling on a pillow, right, is the minimum energy state where you use the least amount of calories. You still use about 600 to 800 calories to sleep, right? If you are going hungry to bed, right, in the morning, you are probably waking up screaming bloody murder, because in a sleep you use another additional 600 to 800 depending on your metabolism, right, just through the night. Because remember, all of your organs have to work consistently. That includes brain, right, that includes heart, that includes everything else, and the blood is constantly flowing. All of that is using the energy that you get in through food. So equilibrium system is like you can also think about the pendulum that it's hanging, right, on the pendulum that it's hanging. I'm just trying to find the pendulum somewhere real quick. The pendulum that's hanging on the ceiling or somewhere. It's not a pendulum, but whatever. And when it's in the state like that, right, where the mass of the bob is the closest to the center of the Earth as it could be, the pendulum is in equilibrium state. You annoy it a little bit, right, and it starts bobbing up. Now, we are going to model this when we do second order differential equation. We're going to learn why it stops, right? Why is it not going forever like this? And we will see in the case when it's going to go forever. So that's going to be chapter 3 or 4, whatever is it now. It used to be in chapter 2. But it's important to know that the equilibrium state is the state when you are not harassing it, right? It's just there. And then you go and you punch it, and then it goes annoyed, and then it stops again. Final example, which is aggravating that I have to talk about it, but I have to, is that the planet is a ball. Why is the planet a ball? Planet is a ball. Get out. Planet is a ball because every particle of the planet, which is every atom of every molecule, every speck of dust, every rock, everything is trying to be as close as possible to the center of a rubble, because rubble being the whole planet, because that would be the minimum energy state. You have to understand that potential energy is mgh. Mass of the object, are you looking at a speck of dust or a rock? I don't care. It has a mass. And then G, gravity. How large is the planet? How far you get to be from the center of mass, which is the center of the planet. And then also height, mgh. Height is how far away you are from that center which exerts the pull of the gravity, right? So now, when you have all of those concepts together, clearly objects that are the same mass but on a different height will have different energy, and the one that has more energy would like to have the least amount of energy possible. That is why everything is trying to be as close as possibly can to the center of the planet, and then when you have the things rotating, they have to rearrange into a ball. You cannot have a disk, you cannot have a cube, you cannot have anything else other than a ball for the planet or any celestial object for that matter, right? Because that amount of mass, right, is trying, every single speck is trying to be as close as possible to the center, and that's why it's a ball. Now you flatten it a little bit because of magnetic fields and whole other stuff, so it's not a perfect ball, it's a little bit squished ball, but it's a ball, right? And there is a very clear, right? So the planet is in equilibrium. The planet is not changing its shape. So it's equilibrium solution to the problem of the planet. Now, can we make solutions? So these solutions, right, we can talk about stable and unstable solutions. And the question is, can we make distinction between them and what it means for the solutions to be stable and unstable. So now we understood the equilibrium solution. Let's talk about stability. And I would actually have to try and draw the diagram, because I can't really talk about it if we don't have it. So give me an hour, I'll be right with you. multiple colors are very helpful in this case. So the blue line over here is the solution where x is equal to m. The black line, which is our t-axis, is the solution where x is equal to 0. You're going to get triggered, but this is your x-axis, which are the solutions, because our differential equation is dx over dt, meaning it's a t and x axis like that. And x equals m, and then x equals 0 solution, and x equals m solution. The differential equation is going to be of the form, right, f of x. That's the autonomous first order differential equation. So we're going to take a look at the situation where, you know, we have these two solutions, x equals m solution. And guys, if you look at these solutions in here, right? If you look at these, that's your logistics growth. Do we all see that it starts at some initial population, let's say, right there on a population axis? Because you know that this would be your p, right? In a previous differential equations. So x is p. So you have some initial population somewhere, which cuts through population. That creates your p0. And then you have somewhat rapid growth of population. And in logistics, if you studied the last lecture, you know exactly what I'm talking about. In a logistics model, it hits the carrying capacity m, right? And then population flattens out. Whether it's starvation or war or whatever, we don't know, right? But we reached the cap of the resources for the planet, and the population cannot be sustained. So either people die off of its own will because there's not enough food, or they compete for the food, which is a nice way, right, to say war, right? But the population cannot go past the value m, which is the solution, right? And the other solutions we don't consider. We can talk about them, but we don't consider. First of all, these are all negative population. So we don't even look at those, right? Very good. And then on top, we have that if by some miracle, right, you are to start with the population that it's way above the carrying capacity, you see that they rapidly decay to carrying capacity, right? So let's say Mars is much smaller than Earth and not habitable until we build the structures, because everything there is poisonous to us, including the soil. Air is poisonous, soil is poisonous. So we cannot live on Mars unless we cover the surface, right? You do not get to walk on the soil. You do not get to drink water. There's no water, but you don't get to do any of those things. But let's say that somehow we manage to terraform the whole planet, and it looks exactly as a copy of Earth, but it's smaller. And then somehow we move all of the people from Earth. 7.6 billion that we have right now, 6.3 billion that we have right now, able to pack everyone and move to Mars. You actually get into those solutions because carrying capacity of Mars, you cannot have, there's not enough water, right? There is no, you would have to go really, really deep down to find frozen water, and still not going to be enough, right? So the carrying capacity of Mars is way, way smaller than Earth, obviously. So you would have the situation which are the upper solutions, and they would rapidly decay to a population of 10 that Mars can support. I don't know. But I'm just tossing whatever. Okay. So we're going to take a look at this, and the differential equation that goes with this one is dx over dt is equal to kx m minus x. Guys, this is exactly your a minus b
birth minus death.
Birth minus death model. Very good. If you take a look at this, right, you can write this as kmx minus kx squared, which earlier we had as ap minus bp squared, right? So you know that's that equation. It's just written in a form of carrying capacity and rate of multiplication, right? So those are the two constants we care. So we can transform one model into another. You can either count the babies and count the dead, or you can transform it into and look at it in the cases of right. So they're equivalent. So let me see. So first, the definition of a stable solution. So a stable solution, where is it? Yeah. So stable solution. A critical point x equals c. Anytime I say x, in your head you can translate that as p. Population equals 5,000, 5 billion. So a critical point x equals c of an autonomous first order differential equation is said to be stable provided that if the initial value x0, talking p0, population, right, is sufficiently close to c, then x of t, in our case population, remains close to c for all t larger than 0, so for all times in the future. Now, they do give you a typical calculus 1 limit definition epsilon delta argument, which makes this even more confusing, I guess, right?
What kind of looks like the Taylor series on, or the range of convergence?
No, epsilon and delta definition from Calc 1, 2.7.
Oh, no, I'm sorry. I was thinking of earlier in the 2.2 chapter.
Yeah, it was, that's a different concept. Yeah. So, so stable if for each epsilon larger than 0, there exists delta larger than 0 such that x0 minus c is less than delta, implies actually I'm going to write it the same way it's written in calculus 1. X of t minus c is less than epsilon whenever x0 minus c is less than delta. Those of you who took honor Calc 1 class had to memorize this and do problems. Non-honors, you didn't do problems, you still had to memorize the 2.7 definition. If you have your calculus textbook, take a look at section 2.7. This is definition that it's in there, the purple one. Now, the purple one says the same thing as the red one, except the red one is closer to what we're dealing with, and the purple one is just a general statement. And the second part, unstable definition. And I always love these. If the solution is not stable, then it's unstable. I always love those. If the solution is not stable, meaning it fails the conditions from up there, then it is said it is unstable. So if you are not a human, there you are a non-human. Right?
Wait, what's that after it? Is it a B or is it is?
Where?
Did you just wrote down?
You're talking here?
Yeah, then.
It is said.
Oh, is. That's
It is said. It is unstable.
So one question about the epsilon delta. The epsilon is supposed to represent the actual function. So when you put in something for t, it should be less than what epsilon is.
The epsilon is insanely small value, and it can be small as you want it to
But that's
be.
going to be the product. That's what x is going to replace. So it's going to be t to the x should be epsilon. And then
Epsilon represents the difference between the solution and try this. It should represent the difference between the solution and the equilibrium solution. That's why it says it's sufficiently close, meaning that the distance between them is closing. That's what in the limit what the squeeze means.
yeah, remember that the epsilon delta is just completely arbitrary. That you just choose something to plug in for the epsilon for the delta.
Yes, which through the calculation, but then you can pick a threshold for epsilon, and there must be a delta that would fit within, because you can make it as it's just it has to fit in between. You don't have tolerance on both sides. You have to fit within that too. So when you pick an epsilon, you have to find a delta that would work, and then we're good, right? But if you're not able to find it, right, it's going to be outside the borders, and then there is no limit.
Okay.
So when you translate that knowledge into differential equations here, you have one curve, and then you have another curve, and it just needs to be constantly that close. The distance between these two must be smaller than epsilon, and epsilon depends on a delta, which is the input, and so on. So this is because now you are not looking for the distance between two y values like you used to look in Calc 1. The limit, right, the way I teach the limit in Calc 1, and those of you that were in my Calc 1, you know that I say this all the time, limit is the fancy way to compute the y value, right? So the limits technically give us the y values from the function. And epsilon and delta there were, delta was the difference between two x values, and that when it intersects the function gives you the difference between the two y values, and the difference between two y values was epsilon. Now it's different. Now the epsilon is the separation of the two functions. There are two curves in a space, where one is the equilibrium solution, right? The other one, critical point, and the other one is a solution. So if they are always close, then the solution is stable. If they are not close, right, then the solution is unstable. So we just need to take a look at examples so this can make some sense, right, in the context. You think he's itching to destroy? You just want to add more?
Just means I have to use a different writing utensil.
Oh.
I'm not allowed to destroy it.
Oh, but I am.
Yeah.
Oh. There we go. So
Oh,
now you
thank
can
you.
use whatever you want.
All that hard work.
Yeah.
Thank you.
So we are supposed to consider, as an example, the explosion/extinction equation, which is the one we had before. So dx dt is equal to kx x minus m, but in this solution we are not going to have that negative on the k in a solution, which would make the population, if you replace x with p, decrease and the extinction happens. We did discuss that briefly last time. I will repeat it. Let me just copy this x of t. You know what? I should just change this into a p, since we talked about population. The book has x's everywhere, but I'm just going to change it into a population, because that's what we understand as a solid example from last class, whether you studied or not. Yeah. Everything else is going to be much worse than this. We have our carrying capacity of the planet M, which is the absolute amount of population that we can have, whether you're talking about humans or zebras. Here's your initial population P0. If you don't know those values yet, write it on the side as a legend, right? What's what? M, carrying capacity, P0, initial population. Then we have our P0 plus M minus P0 e to the positive k mt. So now, what we talked about before was that, and I think I drew these graphs, hopefully I did, e to the k, where k is bigger than 0, gives you growth. 1 over e to the positive k, where k is bigger than 0, but see k is below, is giving you decay. So if I have a positive k, but e with that k is below, is in the denominator, you have a decay. So this is no longer population growth model. This is extinction model, because given enough time, the population is going to go to extinct. And we talked about it. We said for some animals, they said unsophisticated animals. Unsophisticated animals, we don't talk about human sophistication. We are talking about a species where they live so far apart that the female has to look for a mate for a very long time, and sometimes she doesn't make it, right? And we also talked about the female being way more valuable in seeing through mathematical model than a male, because the female has the limit of how much offspring she can produce when the male can reproduce. I mean, male can impregnate the females, right, at a much larger rate than the females can reproduce. So it's a female that is a limiting factor across all species, right? So when we have issue with the female population, we have issue with the species, right? So, and I think we did that example, right, with a 200 population, and then we said half, right? So, and then we saw what happens with the final population numbers after a year. So now, over here, when this k is positive and this is down, and you send this to infinity, right? Then this term becomes infinity, because e to infinity is infinity times some number. I don't care whether your carrying capacity is 1 billion or 7, right? It doesn't matter, right? It's going to be a number. Tie infinity is infinity. Add a little bit more, still infinity. Divide anything by infinity, and the population is 0 eventually, right? So that's why it's called an extinction model, where when you put a minus here and you send it to infinity, this term becomes 0, kills that. P0 cancels P0, and you get your carrying capacity for the planet, for the species, right? So the sign of K is very important. Now we always take, so it's easier on us, right? Because K could be 3, could be -3. So to make it easier on us to do the analysis, we always keep K positive, and then we stick or take away a minus sign. So do you want a logistics model that shows population growth and then hitting carrying capacity? Stick in a minus. If you want to talk about the extinction for a certain species, you take that minus away and you have your extinction model. Now, to talk about stability here, so all of this that I said now is explained again in words. And I'm just going to say, since this is, I'll point the blue with the note. Extinction model. K larger than 0 and no negative, right? So now, when I shoot the limit t goes to infinity, we get of mp0, p0 plus, I'm already regretting for writing this again, kmt, there we go. This term will go to infinity. As soon as that term goes to infinity, we get the whole thing equal to 0 in extinction model. Now, something very interesting happens, and that is, right, this is the extinction model, and we know that this is the solution to the differential equation, and we solve that differential equation because we have births and deaths, right? Now, you should be able to trace this back, this calculation, you should trace this back to the fact that in order for this to happen in nature, there has to be more deaths than births. And eventually extinction happens over time, right? So there is a constant tug of war, right, between births and deaths, and we connected that to the carrying capacity and the rate of introduction of new units to the population, babies or cubs, whatever, which was K. We did say before that the K well, they have it kxm minus x, right? Which I connected that to kp m minus p, and then I said kmp minus kp squared, and then we said ap minus bp squared, from where you can make a connection that b equals to k, and if b is equal to k, then for the first coefficients here, you would have that km is equal to a, but k is b, so bm equals a, from where m is equal to a over b. So we see a direct link where a and b were linked to births and deaths, and k and m are the constants, right? So this transformation helps us understand that part. And now what we can think of is the situation where the initial population, if the initial population is larger than the carrying capacity, you immediately see that the population has to so it will behave opposite, right, than what we have for the regular logistics equation, right? In regular logistics equation, we had that solution earlier that if your initial population P0 is larger than the level at which you have the carrying capacity, the graphs over there show the rapid decrease in population to meet the carrying capacity of the planet, right? And that is for our logistics growth. But what happens with the extinction is completely opposite, which must make sense. If the population in an extinction model, if initial population in extinction model is bigger than the carrying capacity, common sense would say that over infinite time should shoot to infinity, right? Because it has to be opposite to this, because you're using the opposite model. So it has to behave opposite, right? Now, clearly that does not happen because it's extinct, right? But mathematically, right, you can just run the limit and see that you would get infinity there. So we use the limit, right? We use the limit to just show which way the solution is going to go, right? And if it hits the solution, it's stable. We, as a species, are climbing very rapidly to hit the carrying capacity of the planet. Our scientists are not agreeing what that number is, but our rapidly inclining population will find out, okay? Give it 30, 40, 60 years, we're going to hit it, right? We'll see what happens, right? And then we'll know what it is. Right now, a lot of theories out there, anywhere from 10 to 15.2. Those are the numbers that I have seen. And I believe that Jordan Peterson even mentioned in one of his interviews that it's somewhere in 9s. We're going to reach 9 in like 10 years, right? So, yeah. Anyway. So that's the stability, right? You look at the solution, and you can take the limit to see if the solution is stable. Interesting modification to the problem, which is the next subtitle, is harvesting. So let's say you like salmon and it's farm-raised salmon, right? So what is a farm-raised salmon? It's a huge pool where they throw a lot of fish in and they wait to make more fish, right? And then you harvest. Harvest means you take a lot of fish out, you got it and you sell it, right? But you don't take all of the fish out. you take some of the fish out, and then the leftover fish is still going to die off of the old age or off of the lack of food because they didn't get to it, or off of the disease or something, right? There are reasons for the fish to die, right? But they also have birth. So the ecosystem has this huge amount of fish inside, and then they multiply, and then you have even more, and then the net comes in and scoops out, I don't know, 1/2 of it, and then that half is going to multiply again after some time. The net comes in and scoops half, right, and so on. So that's harvesting, right? When you have an apple tree and there are apples ready in September, you don't take the tree down, right? You harvest the apples and then they grow again next year, right? So it doesn't happen with everything, right? For certain plants, right, we kill the whole plant and then it's replanted and it grows from scratch. But for apple tree, you don't do that. So certain things would have harvesting as a model. The other one would be like wheat, right? It's extinction, right? You kill the whole field. There's nothing there. And then you have to go and put the seeds from scratch. So that's extinction model, right? Where if you talk about the salmon farm or the apples, that's harvesting. So now, harvesting model is going to have the same model we had so far, and you just add another parameter minus age. And we want to see what that brings to the table, right? So harvesting. So when you have harvesting, we start with some population in time is our good old, they are using X's in the book. I'm switching to P because it's easier to think. So I don't care if you want to think salmon or apples, just go with that. So we have our AP minus BP squared, and now we are going to take away the harvest. Now harvest is positive. You are not going to pull out, right, negative 35 salmon, right? You're going to pull 35 salmon, not negative 35. So common sense is the age must be positive. For that matter, A and B are also positive too, but we know that from before. In mathematics, there is a success and a failure. I'm not talking about grades, I'm talking about the concept, which is not reflected in your opinion what you think about birth or death, right? So if you are talking to your mom and you're talking about birth and death, generally birth is the positive concept and death is a negative concept. And then you're going to say birth is positive numbers you're adding to population, death is a negative number you are subtracting from population. Fine. That is all good when we talk. But in this case, A is a positive number for birth, B is a positive number for death, because you will be subtracting minus BP, right? Mm-hmm. So you have to understand, you have to separate, right, the everyday talk from what the parameter means. A lot of people get really confused when they look at a parameter and say, why is my death rate positive here? That's not a positive concept. No, nothing to do with the concept, right? A lot of you get triggered when you go to statistics and they say, you know, when the insurance company is calculating something and they say, you know, if the person so-and-so died in the accident, so-and-so, blah, 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 and then they label the death as a success, right? And people are like, what? What did they just do? It's a mathematical term, so you can do your probability. There is a success and failure in the equation, right? So if they were looking for deaths and they find the death, they successfully found the death. It's not like, woohoo, person is dead. It is, woohoo, we found what we were looking for, so we can do the problem, right? So harvesting has to be a positive number because you're going to pick positive amount of apples, you're going to take a positive amount of salmon, and then you are going to see new fish coming in, and you are going to see fish die as well. Disease, no food, or overcrowding, or whatever, right? So there's that too. Good. So now we have this, and I am just going to write down the solution for this. There is no way I'm wasting like 3 hours to go through calculations. So the two solutions are labeled as capital H and capital N, and you'll see why there are two solutions. So two solutions, capital H, comma capital N. In the past, you just had the P because it was a single solution. And here is the solution. Km, remember that you can go to K and M from A and B. There it is. You want your KMM for A and B. There they are. So K times M plus minus the square root of Km squared minus 4HK divided by 2K. You are all recognizing quadratic equation there, right? It's just in these crazy terms. And that can be simplified by simply canceling K everywhere. And it gives us 1/2 M plus minus square root of M squared minus 4H over K. So that's the simplified answer. So now, since you have the two solutions, right, you can plug that back in the differential equation. We used P, not X's. P over dt is equal to K n minus P and P minus H. There we go. One is flipped to just combat the negative sign. And when you set for critical points now, when you set this for critical points, right, when you have the whole thing equal to 0, you have the solution of population equals n, and the solution of population equal h.
I got a question.
Yes.
Back up there when you're can you go a little? Like, why is 4h divided by k?
Oh, because you are dividing by k squared. So from the first parenthesis, k squared is cancelled completely. From the second parenthesis, you only have 1k.
You square K to stuff it under it.
Right? To put this k under the square root, it comes in as a squared. So this k over here is squared already, and it cancels completely.
Yeah.
And the second k is not squared, so there is an extra k that's going to be floating around under the radical. So now you have your two critical solutions here, and your critical solution H, let's say, is going to be the one with the plus. Critical solution N is going to be one with the minus, because that's your H and N, right? And you have those solutions here in terms of the carrying capacity, in terms of the harvesting, which is how much you are picking, how much you're pulling out from the pool, right? For the over harvesting of oceans, right? This is something that people can do to make arguments for overfishing the ocean, right? You pull too much chicken out of sea, which is called tuna, right? You pull too much lobster, right? And all of these kind of things. It can lead to extinction, right? So that factor right there, when you know how much is harvested, right, is something that you can use in calculation if you are into, biology. Let's say you are a bio major and you are interested in population, but you want to write a scientific paper, right? Because when you have a scientific paper, then the policies can be made, right? Clearly for harvesting of a deer in New Jersey here, that number is way negative, right? It breaks the model. It's so negative that it breaks the model and pretty much everyone's car. Someone wrote an equation which proves that if you live in New Jersey, I don't remember what amount of years, you are 100% guaranteed to hit the deer. How about we do the pool? Who hit the deer? At least a little bit in New Jersey so far.
Not yet.
No, not this. You did or you did not, right?
I wasn't driving yet.
Okay. So I had a near experience and a total loss, right? Those are the two encounters I had.
Total loss for your car or for the deer or for both?
I couldn't find the deer. I think I pushed in another dimension. I was going minimum of 60, and the car was, I drove the car back home for another 8 miles or so, but then the insurance company decided to total it because check engine light came on. I was like, all right, fine.
So
First they told me $5,000 to fix it.
So it's
and
like
then-
success woohoo or
Yeah. It's never success, yoo-hoo. Okay. So when you have these values, right? Now you can do the analysis, and you can see whether the harvesting would kill off the population, because it can, right? Harvesting can kill the population. What is an apple on a tree? It's a seed for a new tree. If you never plant a sapling for apple tree, and you never let the apple to fall down into the ground to deposit the seed for the new tree, if the apples are constantly harvested and never ever planted another tree or put the seed from the apple, right? Because that's how the apple multiplies, right? Apple tree tosses an apple, apple has the seed inside, the new tree grows. If you constantly harvest all the apples, then the species of apples would be extinct because you harvested 100% without new birth, right? It's not a birth for the apple. It's the birth for the tree, right? So the female there is the tree, okay? That's what the female is. It's not the apple, it's the tree, right? Okay. And now bifurcation is more of, as I said, a graduate level kind of concept. Is shoved all the way in the back of the lecture for about half a page, to tell you that the solution could be nice and stable and unique, and all of a sudden you reach some critical point, and then it splits into a number of solutions, which in our reality might have different situations. For instance, one of the things where I worked on bifurcation diagrams was dynamics of pneumatic liquid crystals, which are used for LCDs. Very good. So LCD display consists of the very thin rods that orient themselves with the increasing and changing whether magnetic or electric field. So if you want to let the light go through this liquid crystal display and then shine light so you can see the screen, you use the magnetic field, right, to turn those liquid crystals, those rods, and then the light, which is the LED light in the back, right, the LED backlight, shines through the crystals outside, and you can see the screen. You adjust the crystals, and they give you the different levels of light, different colors, and so on, right? So those calculator crystals, right? I'm not talking about the colors. I'm talking about the monochrome ones, right? They're all black or nothing. Well, those liquid crystals are closed or open, right? That's it. But the nice colorful screens you have in your phones and so on, they adjust. There is bifurcation that has to be taken into the account for those, because there are critical levels of the screen, because obviously it's in a magnetic field. You ever want to ruin the screen? Put some very strong speaker next to it, and you will see, right, the green starts creeping in, right, and the screen is ruined. And that's a permanent damage, right? So you can take, if you have an old screen you don't need and you want to, practice these kind of things, take a strong magnet from a speaker like this, right? You have when you have these larger speakers, when you rip it apart, it's going to be a large magnet in the back, right? Especially if you have those subwoofer speakers that are very heavy. What's heavy is the big magnet in the back, right? That creates deep tones. Take that and just, go on the computer screen and or your TV if you don't need it, right? And you will be able to ruin it, right, very effectively with that, because that's how they work. See you next week.